is Koi, and today I'll present about LAMPAT low-rank adaptation for multilingual paraphrasing using adversarial training. So we know that the paraphrasing have enhanced many NLP applications from machine translation to information retrieval to the reading comprehension and the summarization. However, we see that most of the work now focus on the dominant language, which is English. There are some notable multilingual paraphrasing generation works that have explored the multilingual machine translation model, such as the Thomson and Post in 2020, in which they have trained the multilingual machine translation model and infer them using a special heuristic blocking algorithm in order to generate a diverse paraphrase in many languages beyond English. In this work, they have used the algorithm to banalize the model, not to generate the output that is identical to the original input. There are also works proposed by Gu et al. In 2019, which leverage the translation language model objective to model multiple languages. And you can see on the figure A here, the model used is the encoder of the transformer, and it is used to learn the representation between two parallel sentences. While during the zero-shot inference, the language tag will be the same as English and English in order to have the model to paraphrase the input. However, these methods suffer when applied on low-resource languages. We know that the parallel dataset is one of the requirements for constructing the multilingual machine translation model, and the parallel dataset is quite expensive to collect, especially for low-resource languages. In addition, using the zero-shot translation, the output is often lack of novel change in the grammar or word replacement or sentence structure. As you can see in the example here, a human can change the input from like to eat into my favorite food. However, for the zero-shot model, it will likely to replace the to eat with eating, or it could write up a new sentence which does not convey the same semantic meaning with the original input as underlie. Due to the blocking algorithm, this blocking algorithm heavily depends on the vocabulary distribution. In C, for a sequence like I like to eat pasta, the model likely to generate the sequence I like eating. However, as the last token between pasta and paste, it choose paste over pasta because this is where the heuristic blocking algorithm came into work, and it was blocked in order not to generate the identical sequence to the original input. Therefore, the second highest probability token was produced and is totally give the sequence another meaning. Therefore, our work here, LAMPAT, aimed to solve the previous problems that were possessed by the previous work in multilingual paraphrase generation. LAMPAT does not use the parallel corpora by learning in a self-supervised way. The noise perturbation and virtual adversarial learning was applied in order to generate a more lexical diverse sequence, and will also expand the evaluation dataset to 13 languages in order to stimulate further research into multilingual paraphrase generation. LAMPAT consists of two stages. The first one is to generate the synthetic test dataset, where we have firstly the test dataset was a set of sequence. Then we apply a series of processes, identifying the stop work in each sequence, removing them, and randomly shuffle the words, the the remain words in order to create the corrupted version of the sequence. This will create a synthetic data set, which consists of the source is the corrupted version, and the target is the original sequence, where we aim to train the model on reconstructing them. So the model we choose is the causal language model, which is trained using the LoRa adaptation, the LoRa adaptation, and the virtual adversarial training on this newly created synthetic dataset. The final dataset will be denoted as LAMPAT. In order to train the LAMPAT, we first have the input is the original sentence, like the book is lying on the table. Then we have the corrupted version of it is lying table book. After booting through the text embedding, the noise perturbation delta will be added to it and will be booted through a series of transformer blocks in which the query and value matrix of the attention block was enhanced with the LoRa adaptation. And finally, the last will be the combination of the reconstruction loss and the adversarial loss. The reconstruction loss is the loss when we transforming the corrupted version into the original sequence using cross entropy, while the adversarial loss is the loss during approaching a lexical diverse virtual label. The virtual label here we use is the f, x, and theta in place of the original true label y. We also stimulate further research into the multilingual paraphrase generation by extracting one side of the test parallel translation corpora from WMT19 in order to generate the input-only type of the evaluation dataset. We also have a second type of evaluation dataset, which is the input and reference, where we extracted from the multilingual paraphrase identification dataset, from the paraphrase generation dataset, and from the machine translation dataset in order to construct these input reference dataset. The main result. For the main result, we report over 4 to 6 matrices. For the 6 matrix, among the baseline DAE, which is proposed by the work in Gu et al. 2019 and MMT proposed by Thompson Post 2020. As you can see, our method have outperformed the baseline by a large margin in both the input-only evaluation dataset and the input reference evaluation dataset. We also conduct the human evaluation in order to assess the output quality. As you can see here, LAMPAT achieved close to human on semantic preservation, but it still have a lot of room for improvement on the lexical similarity. However, its performance outperformed the MMT by a large margin. So thank you.